July 1st, 2021. Welcome to ORCA 5. Today is a day that we have been waiting for a very long time, and I'm sure many of you have too. My name is Frank Niese, and today I'm coming to you as a delegate of the ORCA development team. Before I say anything else, please let me say how privileged I feel and how proud to be a member of this team and to present to you today what we have achieved over the course of the last 18 or 24 months, but in the long run, more than 20 years that have gone into program development. And without anything else, please let's get to it and welcome ORCA 5, and I'm going to show you what we have done. So, ORCA 5 is a major improvement over all previous ORCA versions in terms of performance, numerical robustness, and workflow optimization or user friendliness, and I hope that you will experience it too. Actually, to the user, ORCA 5 doesn't look all that different like previous ORCA versions, but the changes that were made under the hood are vast and massive, and I hope that you will experience it when you run your first ORCA calculation. And in this talk, I will walk you through the new feature and the major changes and improvements that have been made. So first of all, let's talk about infrastructure and performance improvements. And perhaps the biggest one is the new Shark engine. So the new Shark engine is a new integral generator, but it's not only an integral generator. It generates integrals at very high efficiency, much more efficiently than previous versions of ORCA has, but it's also a task organizer or workflow organizer that lets developers write code much more efficiently, much more cleanly, and in a much more compact way. So to us, it's a new paradigm for quantum chemical code development. And based on what we have achieved with Shark, I believe future program development will be much faster. What we're giving you with ORCA 5 is just the first step. So we have made very large changes, but much larger changes will occur in future ORCA versions. So let's welcome a new start. Now, what you as a user will see from Shark is not much. It's basically a new banner in the output when the integral generation starts, and a few printouts here and there. But everything, nearly everything in ORCA 5 is driven by the Shark engine, and I will talk to you about what's under the hood tomorrow in the more detailed presentation. But that is not the only thing, far and away not the only thing. And one major thing that will change the way you will use ORCA is you will recognize we have new grids for density functional theory, and we also have new grids for cos-X, the chain of spheres exchange that is accelerating hybrid DFT calculations and Hartree-Fock calculations. And this was necessary because the old grids were outdated and they were a bit clumsy to use. There were many different grids in different parts of the program, and we felt that a major redesign of these grids is necessary in the interest of giving you, by default, much more accurate grids so that users will not have to change the grids manually all the time. So that also means that the old grids are no longer available. You can redefine them by hand, but actually you shouldn't, because the new default grids are really good. From now on, there will be only 3 grids available, and they're called Def Grid 1 to Def Grid 3, with the default being Def Grid 2. These grids are larger than the old grids, but they're much more accurate, and that is what you really need, because getting a bad result fast doesn't mean anything. All subsequent grids for CPS, CF, TDDFT, GIAO, cos-X calculations are chosen and adapted automatically. Also, these grids self-adapt them to the basis sets that you offer the program. So if you have steep core polarization functions or similar things, uncontracted basis functions, these grid will notice that and they will self-adapt. So there basically is no use anymore for features like special grid that many of you have known from previous ORCA versions. The user can still manipulate the grids, but we do not recommend to do it. Grids necessarily lead to numerical noise and errors, but we have tried our very best to keep these errors as small as humanly possible. So with these new grids, with Def Grid 2, you get energies within 0.05 kcal per mole, for cos-x and 0.01 kcal per mole of the grid limit, of the infinite grid limit with DFT. Frequencies are accurate to 0.04 wave numbers with cos-x and to 0.1 wave numbers roughly with TFT. And excited states are accurate to a tiny fraction of an electron volt with these grids. So essentially these errors are vastly insignificant compared to all the other error sources in the calculation. So in principle, with these new ORCA 5 grids, thinking about grids is a non-issue anymore. Just go with the defaults. The same holds for the chain of spheres. The new default is at least as accurate than grid X8 that many of you have been using in your applications, but it's much smaller than grid X8. So the cos-x became so accurate and so good and so fast that it's now the default for all hybrid and double hybrid DFT calculation. And you will certainly notice that in the performance when you just simply type B3lib, you will get the cos-x version, and the cos-x version is accurate. Now, we have not only improved the grids, but we have also vastly improved the efficiency of the integrals, of the analytic integrals that are part of the chain of spheres exchange calculation. And speedups range for at least a factor of 2 to almost a factor of 10, a full factor of 10 compared to the integrals that we had in the old code. Now, with all that, let's look at some benchmark numbers that we have collected in the preparation of this talk. So first of all, let's look at the integrals. Now, pure DFT calculations that do not feature Hartree-Fock exchange, they still rely on the Rij approximation. And we had a particularly efficient variant of the Rij, which we call the split Rij, and it was produced in 2003. And that 2003 algorithm was extremely efficient, and it was a very difficult job to beat that, but we have. We have redesigned that algorithm, that Rij algorithm, as you can see from these numbers here for vancomycin with the PBE functional. The new split Rij implementation is even faster than the already very fast old one, in particular when the basis sets are large. We also have a much more efficient engine to drive correlation consistent basis sets that we call partially generally contracted. And it is also vastly more efficient for fully generally contracted basis sets like ANO basis set. And the analytic integrals, they were very good based on the libend package, but they have also been further improved. And you see that in those B3lib timings here that are at least like 20-30% faster than before. And especially when the basis sets are larger, the new integral engine is much more efficient than the old one. Now, these improvements in the integrals, however, they do not fully translate to wall clock speedup times that you see, and that is because of the larger grid. So if you look at all Fock matrix builds, so here we have the same two molecules, 11 to 15 Fock matrix builds on 16 cores, and you see these times are really, really short. So that's it. ORCA 5 is an extremely efficient program. And as you see, in comparison to 4.2.1, the 5.0 numbers, they are typically a bit lower, but not that much lower. But you're getting improved accuracy. So in the default settings, you're getting significantly improved numerical accuracy in your energies, in your gradients, and in your frequencies. And basically the performance improvements that we have achieved with the integrals are partially now invested, so to say, into the higher accuracy of the grid. And again, do not change these default grids. They are accurate and they will serve you well. So for those of you who have by default used larger grids than the default grids, they will experience for sure that ORCA 5 is a much more efficient program than it was before. But we have not only improved the efficiency of the integral generation, but, and that is particularly important, the integral digestion. And that shows up in a major way in Hessian calculations or TDDFT calculations. So when you compare the Hessian calculation times, here they have halved most of the time. We have seen speedups on the order of a factor of 5 in wall clock time compared to the old Hessian, plus getting more numerically accurate results. In TDDFT, the speedups are particularly large, and there with together with large basis sets, you reach a full factor of 10 in wall clock time that ORCA 5 is more efficient than ORCA 4.2.1, which was not a slow program. So we believe that this is perhaps the most efficient TDD-FT that is available, and definitely by far the most efficient TDD-FT implementation that we ever had in ORCA. Now, polarizability and response properties in general, they have also improved vastly. Again, up to a full order of magnitude in wall clock time is achievable with ORCA 5 relative to ORCA 4.2.1. NMR has been completely redesigned. All of the GIO integrals have been redone. This is part of the SHARC package, and other improvements have been made, in particularly in the COSX. And so here's an example, amylose dimer, and now the speedups for all 555 spin couplings is a factor of 6.6 relative to ORCA 4.2.1. That's a real game changer. Also, chemical shieldings have been greatly improved in their performance. There's a factor of 2, sometimes there's more than a factor of 2. And again, this is all due to the highly improved infrastructure that we are providing here with integral generation and integral digestion. For EPR, it's basically the same. The speedups can be very, very large for spin-spin coupling calculations. Again, it's pretty much an order of magnitude. And for G-tensor calculations, the spin-orbit coupling integrals have been strongly improved, while also implementing GIAOs. So to give you better numerical accuracy, factor of 2 is a typical speedup that you'll see relative to ORCA 4.2.1. So now about user friendliness, and we have made some major efforts really to make ORCA more user friendly. Computational chemistry often is an expert territory, and if you know a program, then you have to know like a gazillion keywords and combination of keywords that give you the best possible results and performance. But we wanted to make it even simpler. We wanted like all entire work groups or groups of individuals working together, or even for the individual researcher, to give you something where a single keyword replaces a long chain of keywords. So basically to build the expert knowledge that people have into the ORCA input. And that it happens via a compound scripting language. So compound scripts are simple ASCII files that implement protocols. And these protocols can be applied to series of molecules. So basically, rather than typing 500 times during the course of a computational chemistry study, B3lib, def2, TZVP, def2j, etc., you can put all of this into a compound script, and then you run that job from a single keyword calculation, and it will execute all of these steps. So for example, you can write a compound script for geometry optimization and frequencies with method A, solvation with method B, and then electronic energy with method C, and then put it all together and provide a nice printout that the user sees in the end. We have given you 2 or 3 dozens of default protocols that we are using, and they also include high accuracy energy protocols like G2 to G4 and CCCA and etc. We also have provided, and I'm showing you that in a second, a script that does iterative geometry optimization. So if your geometry optimization lands on a saddle point and has negative frequencies, that's annoying, because in the previous times you had to then displace the coordinates by hand and re-optimize until you found a real minimum. Compound script lets you do that with a single keyword. There are default variables in these compound files that can be overwritten from the ORCA input, and it also has real programming language features. So it has if statements, else statements, for statements, goto statements, printf statements. System calls can be made out of the compound script. So it's a really extremely powerful way of organizing your computational chemistry workflow. And you also have full access to all of the properties, and these are about 200 different properties that are stored in the ORCA property file that is an ASCII file, so it's human readable, or it can be read by any analysis script that you want, but you can also integrate that into your compound script. Let me give you an example here. So the first example here is just the CO molecule with CCCA, CBS, one high accuracy energy protocol. And so what you see here, that you simply have to type percentage compound and then the name of the compound script, and that's it. And then the program will perform 7 distinct steps, starting with geometry optimization, then MP2 CBS calculation, covalence correlation correction, etc. And at the end of it, you get a nice printout that is summarizing all of these components, and it gives you final energy that you can then use to put in a table. And of course, you can also run series of molecules through these compound jobs so that you can automatically run large databases or benchmark sets with very, very little opportunity to make human error. And that helps computational chemistry studies in a very major way. Here's the example that we actually picked up from the ORCA forum. It was a molecule where the starting structure, the optimization converges to a saddle point. And then in here we show you how the script can be used to find an actual minimum. So here, the example that I'm giving you, so you call the compound script iterative optimization.cmp, but then just to show you how that works, you can override some of the default variables, and one of those variables is max n tries, so it's the maximum number of tries that the program makes to find a minimum, and that is set to 20 here. And if you want a different base name for your job, you can also do that. And so you can set strings, and that base name is then forum example that you can also override. Again, you don't have to override it. All of these compound scripts have default values, sensible default values for these variables, but you can override them. So here's the example. So you start with an initial structure for this molecule that is at 36 kcal, and then the first optimization reaches a saddle point with a negative frequency of minus 643 wave numbers. And sorry, there's a mistake on that slide. The energy is 18.9 kcal. And then finally it finds a minimum that has the lowest energy and that has no negative frequencies anymore. Again, one keyword and the program does the rest for you. And we hope that the ORCA user community is greatly embracing these compound job facilities, and tomorrow you will hear a full talk on this. Now, there are new features in DFTs and basis sets. So we have incorporated the latest libxc density functional library that contains 588 different density functionals. So you have all the choice you want, including range-separated functionals and double hybrid functionals for energies, gradients, Hessians, also DDDFT gradients. It also includes a new scan functional that has gotten a lot of attention lately, and also Stefan Grimme's accurate and low-cost version of it, the R2Scan 3C. In addition, we have implemented the analytic gradient for the VV10 dispersion functional, and we have implemented analytic frequency for meta-GGAs. That was something that our users have asked us for quite a bit. In terms of basis sets, we have finally developed the SARC Zora basis and DKH basis sets for the second row transition metals and some other elements. So they are now pretty much available for the entire periodic table. And we have added some other basis sets like partially augmented Dunning basis sets, relativistic basis sets. We have also defined a ghost track keyword for easier counterpoise calculation. Now, solvation is another thing where a lot has happened under the hood. So we have implemented the Gaussian charge scheme throughout ORCA and throughout all of solvation, and that helps the numerical stability of calculations a lot. So geometry optimizations get much smoother, and also the analytic frequencies are much more reliable in that scheme compared to traditional schemes that rely on point charges on the cavity. So we have analytic first and second derivatives of the FCF energy. We have implicit solvation in coupled cluster calculations. That was also something that was missing from ORCA, including DLPNO CCSD. So now you don't have to mix and measure DFT solvation energies with highly accurate DLPNO CCSDT electronic energies. You can incorporate like your solvent scheme like CPCM or SMD straight into the coupled cluster calculation. We have also parameterized free energy of solvation calculations for the Gaussian charge scheme for organic solutes and different solvents. And another thing that was missing in ORCA so far, but is available in ORCA 5.0 is the linear response PCM gradient and energies for TDD-FT. So major improvements here too. There have been technical improvements, also something that was requested a lot in the forum, and particular memory handling. Very large DFT jobs got very, very memory consuming, and then when you parallelize that, the machine easily ran out of memory. So we have made quite some efforts to use shared memory for key quantities and those that consume the most memory in these calculations to distribute that over a multi-core machine. And the shared memory is used all through Shark and in most other parts of the program. Of course, ORCA hasn't been and will not be a fully shared memory program, but we believe that we have eliminated some of the most important bottlenecks, and I think that is an important development. Another thing that very large calculations had problems with is that we ran out of the range of 32-bit integers. So now ORCA 5 is fully converted or nearly fully converted to 64-bit integers, especially all of Shark and all of the matrix vector routines that we are using in very large scale throughout the program. They all feature shared memory now. We have also upgraded to the most modern libraries, OpenMPI 4.1 and OpenBLAST with AVX 512 support. One last thing that we have done, and that was also requested quite a bit in the ORCA forum, was that we have provided a better interface to ORCA. So there is a new program that's called ORCA to JSON, and what that does is to convert GBW files and other things that are in the GBW file to JSON format. And I know that many of you are fans of JSON and will be able to pick up the required information there. That is something that we will have to extend in the future. We also plan to run it in reverse. This present ORCA version doesn't do that, but in the future you will also be able to use JSON in order to import orbitals and other things into ORCA. Now, these are all technical improvements that are of a global nature, and I now wanted to briefly walk you through the improvements that have been made in various of the ORCA modules. So first of all, and that is also a part of the workflow optimization and the numerical robustness, ORCA 5 now features a really robust second-order converger that we call TRA. It's a Trust Region Augmented Hessian approach, and that converges basically everything. And then so anything we have thrown at this, including the craziest transition metal systems with a gazillion unpaired electrons, it will converge. By default, it is a bit slower than the old one for the easy cases, so that's why we have also made quite an effort to come up with a scheme to trigger TRA automatically when it's needed. So the program detects when the SCF convergence is slow or stuttering or jumping or does funny things, and then TRA kicks in and brings you home there into a stable SCF solution. Here is an example that features 4 and O ligands and 2 open shell irons, so 6 open shell fragments, and that has a crazy electronic structure that is very difficult to converge, and you see all of the standard convergers fail, but TRA will converge this eventually and will lead to much lower energy than the default convergers can do. So that is a thing we're proud of, and that we hope you will embrace and use and will experience in your computational chemistry calculation. Now, CIS, TDD-FT and STUM, so there is a whole laundry list of new features for excited states, starting with recognizing symmetry and printing S-squared for TDD-FT. There's population analysis using relaxed densities for excited states. There is collinear spin flip TDD-FT. There is a double corrections also for triplets now. There is a new variational linear response CPCM for TDD-FT that I've already mentioned. There's non-adiabatic couplings, there's optimization of conical intersections, there is the coupling with the NEB functionality to find minimized transition states on excited state and surfaces. There are new transition densities for the STUM, CCSD, and DLPNO, EOM CCSD, which gives you very high accuracy results. The improved capabilities of the ESD module that many of you have embraced and used for their photochemistry studies. And there also is MCD for closed shell from TDDFT and SDEOM. And so we hope that the already popular ORCA, TDDFT and SDEOM functionality will see a significant boost in use due to these new developments, and of course coupled with the vastly improved performance of it. Local correlation has been a staple of ORCA in the framework of the various DLPNO methods, and we have continued to work on this too. So multi-level DLPNO and DLPNO MP2, in OpenShell DLPNO CCSDT, and also in DLPNO IPEA EOM that features multi-level functionality. Then the EPEA functionality has been improved, and there are core excitations density, also MCD and transition and transient absorption spectra can be generated from it. OpenShell DLPNO CCSDT F12 has been added, and there also is an PNO extrapolation that is quite clever, that lets you extrapolate to the limit of TCAT PNO equals 0, and that saves you time while at the same time improves the accuracy of the PNO calculations. There is open and closed shell HFLD, which is another very clever idea that you will hear more about tomorrow for non-covalent interactions in very large systems like DNA fragments. And last but not least, and I'm coming back to that, there is DLPNO MP2 and double hybrid DFT NMR shieldings and dipole polarizabilities. That was a very hard development, and we're very proud that we were able to complete that and pull it off and give it to you now for NMR calculations of unsurpassed accuracy. In EPR NMR, as I said, there are new NMR features. So first of all, the first thing you will experience is the increased efficiency, which is about a factor of 2 for shieldings and about a factor of 6 for couplings, as I've mentioned in the benchmark section of this talk. DLPNO MP2 shielding calculations for large systems. There are vibrational corrections to NMR shieldings via VPT2, so that is also something that has been requested and that we're proud and happy to give you. And you can also now have an actual NMR spectrum simulated. So basically taking the calculated spin Hamiltonian parameters and generating an actual NMR spectrum, so that is will greatly facilitate your comparison with the experiment. There also is a local orbital decomposition of NMR shieldings and an interface to the natural chemical shielding analysis in the NMR program, in the NBO program. And there is a rigorous treatment for the current density dependence in meta-GGA, so something that was a technicality that before we didn't have, but now is available. And so we hope that we see a lot more use of the NMR facility of ORCA. EPR has also seen significant new developments. So now there are open shell magnetic properties at the RIMP2 level, G-tensor, and also the orbital contribution to the hyperfine coupling for double hybrid DFT with or without frozen core calculations, including CPCM and including GIAOs. The efficiency has been boosted by about a factor of 2 to 4, as mentioned before. There are vibrational corrections to hyperfine couplings via VPT2, and that is also something that will many of you like who are involved in magnetism. There is an interface to the NISO program that is very popular in the magnetism community. It has many features that are similar to the magnetism capabilities of ORCA, but it implements some more things that are attractive to that community, and now you can run basically an ISO in conjunction with ORCA. So that's great. QMMM and embedding techniques is something that has been quite a focus of the development in ORCA 5. And the goal here is, of course, to bring ORCA's very powerful high-level methods to extended systems like biomolecules, proteins, DNA, large molecular systems like explicitly solvated systems, and also solids like molecular crystals or semiconductors and insulators. And we have published many papers making use of these features, and now we're giving them to you, and we're giving them to you in a very streamlined and user-friendly fashion. One thing that I think will see a lot of use, that there is a fully native QMMM and a fully native Onion capability in ORCA. So no more scripts or driving ORCA through external devices, and it's all fully native and it's user friendly and it's efficient and it's completely integrated into the program. So we hope that you will see a lot of that. There is conversion tools from popular force fields like Charm and Ember and Open Force Field. There are automated parameter-free Onion models, Onion 2 and Onion 3 models for extended QM regions. And there is a strong focus on usability and comprehensiveness. So ORCA was always a program for large molecules, and now it will become an even more attractive program for extended systems and very large systems. One of these things that we have created in the process is an ORCA utility that we call ORCA Crystal Prep, and that provides an automatically streamlined protocol for embedding calculations for solid. So it's an automatic input generator that leads you directly from a CIF file or an XYZ file to an output that is an ORCA input file that you can directly use to run ORCA. So all of these millions, maybe not millions, but all of this large number of technicalities that you had to deal with manually when running embedding for solids and surfaces and these systems, they can be taken care of by ORCA Crystal Prep in a pretty much automatic fashion. The molecular dynamics module has been strongly improved as well, thanks to our collaborators, and we're very grateful for that. And so now we have added a meta-dynamics module with many features and options. So you will have to consult the manual to get a full detail for that, to run free energy profiles. And there are also other technical improvements like modern and more powerful thermostats. You can now define restraints for distances, angles, dihedrals, coordination numbers, and you can print the instantaneous and average force on constraints and restraints. And so again, ORCA MD is a rising facility, so to say, or constantly improving facility into ORCA, and we hope to see you making more use of it in the future. Now, CAS-SCF and multi-reference perturbation theory, so there are quite some new features. We have been active doing research there. And one of the methods we're proud of that we call CAS-PT2K, and that is a variant of CAS-PT2 that does not rely on any empirical parameters like IPEA shifts. So it basically gets rid of almost all intruder states automatically. And you have no empirical parameters to fudge around with, and we like that a lot. And now there's also exact CAS-PT2, CAS-PT2K, and NEF-PT2 without the need to generate the 4-particle density. And the 4-particle density, as you have probably experienced if you ran large active spaces, was a major computational bottleneck in the old day, and now it has been improved by almost 2 orders of magnitude, the calculation time, if you were bound by the 4RDM. Now, linear scaling DLPNO NEF-PT2 F12 is also available, so you can run large scale, very large scale NEF-PT2 calculations at the basis set limit. And we have also, we are critical of it, but we have added a cumulant expansion for NEF-PT2, including imaginary chef, to address intruder state problems, but by and large we're not really recommending the cumulant approximation, but we give it to you so you can make up your own mind on it. The auto CI is something that has been in the making for a long time, and huge strides have been made in improving that facility, and you will probably see it's in full glory in ORCA 6 when many methods will be implemented automatically via the automatic code generation. With ORCA 5, we give you an improved version of the fully internally contracted MRCCSD that is a monstrously complicated method, but we give it to you, you can use it, and you can probably do 300 to 400 orbitals with it, which is an achievement in our opinion. There are first order properties with single reference CI modules, and I promise the next version will feature all kinds of correlated gradients that we will generate via the AutoCI facility. Now, another major improvement here is the CIPSE or ICE module that is a near full CI method. It is in a similar vein as DMRG or the quantum Monte Carlo full CI, and but it uses more traditional techniques, if you want so, based on selected CI calculations. And we have done something that we found intellectually incredibly pretty. You will hear a talk on that tomorrow. And now you can use 3 different types of many particle basis functions. You can either use configurations, that is what has been there before. This is extremely efficient as long as you don't have too many unpaired electrons. But when you have many unpaired electrons, you can directly work with configuration state functions and get fully spin adapted states. And you can do crazy complicated spin couplings. There are huge advantages for complicated magnetic systems using that. We also have included a determinant implementation of that method that basically will teach you that it is never the optimal choice. So either it's the configuration or the CSF that is the best choice to run these calculations. We have definitely done calculations with 50, 60, 70 active orbitals, so you have access to very large near full CI calculations with that. You can also use that as a CI solver in CAS-SCF, so you can get very large CAS-SCF results. Here's an example for that, where we show you near full CI calculations on a few hydrocarbons, and from this you can see that the results you're getting are very close to CCSDT parentheses Q, and they're more accurate actually than DMRG calculations. There also is now a facility to extrapolate to threshold 0, so basically to the exact full CI result, and that further reduces the error and lets you do enormously large calculations. Finally, there is something that is more targeted towards the X-ray spectroscopy community that make a lot of use of multiplet code. And these multiplet codes, they basically solve an atomic multiplet type of CI problem and generates all kinds of X-ray spectra, including RIGs or X-ray absorption and emission, etc. But it contains empirical parameters, and not only a few. And what we are giving you is a program that you can use standalone, independent of ORCA, as a multiplet program, but you can also generate all of these parameters automatically via the ab initio ligand field theory that we had developed. And so that basically works hand in hand to generate these parameters for you, and you can use them as starting point in your calculations. And of course, a multiplet calculation takes fractions of a millisecond, whereas a quantum chemical calculation can take hours or days. And so you can play around a lot with ligand field parameters or RACA parameters and so on and so forth. We also give you a large database of NeFPD2 pre-computed LFT parameters that you can use to start off your simulation. So we very much hope that the X-ray spectroscopy community will embrace that too. Now, with that, I'm at the end. I've been very quick, so I hope that you enjoyed that little overview here. And tomorrow we will have a full day of talks where you can learn more about the intricate details of many of these things. Again, even a full day tomorrow cannot cover everything in depth, and that's why we encourage you, as we always encourage you, to come to the forum, which is a friendly, nice place for you to discuss and learn more about ORCA and its various capabilities. So my heartfelt thanks go to the ORCA development team that has worked incredibly hard throughout the lockdown. We have been super active here. We have met hundreds of meetings and discussions and forums, and it was a real joy to work with all of these ladies and gentlemen, and I'm deeply indebted to all the hard work they have put in. All the PhD students and postdocs, all the computational chemists who have helped us, given us feedback, improved the program. Then finally, FACTS. ORCA and FACTS is a very close marriage, and I'm super happy that the company FACTS exists and distributes ORCA to industry. And FACTS has been also really, really active in the development and has helped in many, many instances in particular QMMM and the TDDFT excited state facilities, that basically is all done, or nearly all done by FACTS, and I'm very grateful for the friendship that we have. Then finally, the ORCA user community. It's all of you who has given us feedback, who have discussed with us in the forum, and who made our lives joyful and better. And last but not least, of course, funding agencies. The Max Planck Society has provided very generous funding, as well as the German Science Foundation, and we're deeply indebted to those two, because without them, that would not be possible. And so now I hope that you enjoyed that and that you have a few more questions. I leave you with a few seconds of music, and then we will be all there, online, there for you to discuss with you and answer your questions of what is ORCA 5 and what can you do with it. So enjoy the program and take care.